Can a quantum computer find a brain tumor in an MRI scan? I mean, it sounds like something straight out of science fiction, right? But today, we're actually going to dive into a fascinating research paper that explores exactly that. We're going to see what happens when you pit quantum machine learning against one of the biggest challenges in modern medicine.
So here's our game plan for this investigation. First, we'll get into the diagnostic dilemma, why we even need a new approach. Then we'll explore the quantum leap itself. After that, we'll meet the quantum models that are stepping into the ring, watch the quantum showdown, and finally, we'll get to the verdict and talk about what's next.
All right, so first things first, why are scientists even looking at quantum computers for this stuff? I mean, what's the problem we're trying to solve? Well, it all comes down to just how hard it is to diagnose brain tumors accurately and, maybe more importantly, quickly.
Think about it. When a radiologist looks at an MRI, they are literally searching for a tiny, subtle clue in a massive sea of pixels. The difference between perfectly healthy tissue and a dangerous tumor can be incredibly small. The stakes here couldn't be higher. We're talking life and death. You know, this manual process is really a specialized art, but it's got its limits. It takes an incredible amount of focus, it's super time-consuming, and let's be honest, even the very best experts are still human. They can make mistakes, and that's exactly why the search is on for powerful, automated tools that can help them out. But here's the twist in the story. The AI we already have, the classical AI, is actually amazing at this. Some models are hitting 97% accuracy. So that begs the question, if our current tech is already this good, why on earth are we trying to bring in quantum computers? What more could they possibly bring to the table?
To answer that, we've got to understand what makes quantum computing so different. This isn't just about building a faster version of the computer you have on your desk. No, this is a totally new, fundamentally different way of processing information. Okay, think about your phone or your laptop. They run on bits, which are basically like little light switches. They're either on or they're off, a 1 or a 0. Simple. Quantum computers, on the other hand, use qubits. And qubits are more like dimmer switches. They can be on, they can be off, or they can be somewhere in between. They can actually be both at the exact same time. This weird state is called superposition. And this ability, this superpower to explore multiple states all at once is what it's all about. So instead of looking for a tumor pattern in an MRI pixel by tedious pixel, a quantum computer could, in theory, analyze all the possible patterns at once, spotting these really subtle connections that a classical computer just might miss.
So how does this quantum superpower actually turn into an AI that can do something useful? Well, the researchers in this paper put 3 different quantum models to the test to see which one, if any, could handle this massive challenge. First up, we have the QSVM. Think of this one as a specialist. It's really good at drawing a clean line between tumor and no tumor. Then there's the QNN, which is more of a general-purpose, all-around quantum brain. And finally, the one to watch, the QCNN. This one is like a quantum AI that has special goggles just for analyzing images, kind of inspired by how our own vision works. Now, what's so fascinating about this one is that the QCNN is a hybrid. It's a team player. The quantum part does all the heavy lifting on the image analysis, but a regular classical computer acts as its coach, constantly telling the quantum circuit how it can improve. It's a real partnership between both computing worlds. The QCNN also has a secret weapon. A lot of quantum AI models, when you try to train them, they hit this wall. It's called the barren plateau. They basically just stop learning. But the QCNN processes images in layers, kind of like our brains do. And that special structure helps it avoid this problem, making it a much, much stronger contender. So, we've met the challengers. Now it's time for the main event. The researchers took a public dataset with over 7,000 MRI images and fed it to their models. So the big question is, how did they actually do? The first test was pretty straightforward. It was a simple binary classification. The models were shown an image, and they had to answer just one question. Is there a tumor? Yes or no? And the results are in. Just take a look at these top 2 rows. The Quantum FCM, clocking in at 88.61%, actually beat its classical cousin. That's a big deal. And then, down in the neural network fight, the specialized QCNN was the clear winner at 79.2%. A really impressive first round for the quantum contenders. But the next challenge, well, this one was a lot harder. It wasn't enough to just spot a tumor anymore. Now, the models had to classify the image into one of 4 distinct categories: glioma, meningioma, pituitary tumor, or no tumor at all.
And this is where things got tough for some of them. This messy-looking chart is what's called a confusion matrix, and it's for that standard QNN model. All the correct answers are supposed to be neatly lined up on that diagonal line. As you can pretty clearly see, the predictions are all over the place. It was deeply confused, which shows it just couldn't grasp the more complex patterns. But the QCNN, that told a totally different story. Its overall accuracy wasn't perfect, but it was an absolute superstar at something called recall. Now, what does that mean? It means that when a tumor was actually there, the QCNN found it almost every single time. And for a diagnostic tool, that is what matters most. You cannot afford to miss a real tumor.
All right, so after all these tests, what's the final verdict? Which model came out on top, and what does all of this really mean for the future?
The clear winner, the most promising contender, is the QCNN. Its special design made it stable, sensitive, and pretty much perfect for medical imaging. The QSVM also had its moments. It proved that quantum can beat classical in certain situations. The general QNN, though, it's got a lot of catching up to do.
And hey, that's not just my interpretation. The researchers themselves concluded that the Quantum Convolutional Neural Network, the QCNN, stands out as the best path forward for using quantum computers in this field.
But, and this is a really big but, we need a reality check. All of these amazing results came from simulators. These were classical computers pretending to be quantum. Real quantum computers today are still pretty noisy and prone to errors. Closing that gap between a perfect simulation and our messy reality, well, that's the next great challenge. And that leaves us with a final, really provocative thought. Maybe the future isn't quantum versus classical. Maybe it's quantum and classical working together. Imagine a future where a classical AI does the first big pass, and then a quantum AI is called in for the toughest cases to find the patterns that no other tool could possibly see. The future of diagnostics might just be a team effort.